So let me first introduce myself. So I'm Dmitry Skryabian from University of Bath, and University of Bath is a coordinating body for this consortium. And thank you everybody for making this webinar to happen at this uncertain time. And I would like to start by highlighting, it's going to be very short, but I still want to highlight a few things. So obviously our consortium is strongly affected by the pandemic situation because we are experimental consortium. We can just run all our activities from home, and our secondment program and our experimental program and even my theoretical group is affected in a major way by the events of the pandemic, but still I'd like to say thank you to the European Union, to the framework program, so they continue obviously to support and fund our consortium and expect that those activities that we can move online will be moved online. And this is first of such an activities that is happening today, and we hope that this is not going to be the last one, right? So we start basically from your presentation. This is our first webinar, and today's program has 3 sessions, right? About 1 hour. First 2 about 1 hour, and the last one will be slightly longer, 1.5 hours, with breaks in between. The first session will be chaired by me, second one by Professor Inga Brüning from Freiburg University, and third one by Professor Pascual Munoz from Valencia. And Joanna is going to coordinate the kind of technical side of things and say to us if something is going wrong, right? And I'd like to first thank Joanna for helping and basically for taking the main load with the organization of this meeting. And I'd like to now invite Gervais Fan from Bath to make his first presentation. So I'm going to look after the time. So if I say that 1 minute is left, then it is 1 minute is left. Then we have some questions, right? Discussion about the talk, and then we proceed to the next one. And I'm asking everybody, please keep on time, right? So that we're all comfortable about the schedule and more or less stick to it. So Gervais, please.
Yeah.
Yes, so you have to share your screen.
Yes.
So that we can see your slides.
Yes. Oh, wait a minute.
Yeah.
So, can you see my slides now?
Yeah, I can see them.
Okay, cool.
Yes.
So,
yes.
okay. Hello everyone. My name is Gervais, and I'm the first year PhD student at University of Bath, and also as a member of the Microcomb project. And my introductory talk will briefly consist of 3 parts. So firstly, I will introduce myself and our research group. And in the second part about the research background, I will very briefly talk about some research projects that I did in my master period. And in the last part, but not least, I will use several slides to introduce my current research. So first, about me, I'm Gervais, and I joined this project since last October. And my current institution is University of Bath, located in a very lovely city of Bath. The picture on the bottom is our campus without any post-processing, so you can find this is really a nice place to do the research. And the second picture here shown here is taken from Tel Aviv University, where I finished my master degree. And this house is kind of landmark there. As you can see, it's composed of elements from the computer, you can find the main board and mouse keyboard, right? So, okay, next about our group member. Actually, we have 6 members in the group. Professor Dimitris Garbin is our group leader. Joanna is this project's coordinator, and we have 3 researchers to perform this Microcomb project job. So Alberto is the research staff. Danina is the second-year PhD student. Vlad is another Microcomb member, and he will introduce himself later. And the last guy is me. Okay, so yeah, this is our group. And next, about my professional background, I want to introduce this part based on my thesis towards my master degree. And this topic is the dynamics of 2-component solitons in optics and matter waves. And to make everything clear, I made a chart. As you can see, I studied 2 systems, and they're shown in the blue square. And the main feature of each system is shown in the green square, and the major outcomes of the project is shown in the yellow ones. Okay, so let's start from the first case in optics. The model is described by the nonlinear Schrödinger equation, and we considered a dual coupler in 1-dimensional case. And the main feature is that the gain and the loss factors in separate cores are varying periodically along the propagation. And meanwhile, the coupling between the cores is also a periodic function as well. So since all these terms are described by the periodic functions, we have a lot of variables like amplitude, phase, and frequency. So in this work, we studied how these variables affect the stability of the solitons. And as an outcome, we found that these variables features an optimal relation that under this relation, we can have very robust solitons. And this is about the first case. And in the second and third case, I studied the solitons in Bose-Einstein condensates. And this system is described by the Gross-Podolsky equation. And to some extent, the mathematical form is quite similar to the nonlinear Schrödinger ones. In the second case, we considered a 2-layer lattice. It's also in the 1-dimensional, but 2 parallel lattice, and the dipoles can be trapped on this lattice. And the main idea here is that these dipoles should react to the external field. So by controlling the direction of the external field, we can control the orientation of the atoms, right? So in this case, we found that some new families of the solitons can occur when you change when you rotate the external field to some specific angle. And due to the fact that when this added field is not parallel or perpendicular to the lattice, the symmetry of these 2 parallel lattices will be broken. So the symmetry breaking is also included. And the last case actually is a little complicated and not good enough to make a brief talk. But in general, study the case when the spin-orbit coupling energy is quite larger than the kinetic terms in a low-dimensional setting. Due to the confinement of the space, we treat that the atoms as a very heavy ones. And so we neglect the kinetic energy in that setting. And we found there's some new families of solitons. Yeah, and we studied the transition between them and also the dynamics of them. Okay, so this is my previous background, and now actually I'm starting in the Microcomb project, and in this project I want to introduce my motivation first. So probably most of you already know that the symmetry breaking phenomenon is a very typical and well-known feature for the counterpropagating waves. And here I put an experimental result from the highest group. And they show that when the fused silica resonator is pumped bidirectionally, as you can see that in the panel on the top, you have the pump from the left side and the right side. So the clockwise and the counterclockwise waves will have different energy due to the symmetry breaking, and this feature is very useful for a gyroscope. As we know, the conventional fiber gyroscope can detect the rotation speed by a Sagnac effect. Suppose you put two lights in the fiber loop with opposite direction, and you start to rotate the whole siding. The interfered lines will move roughly proportional to the rotation speed from the output. However, in the micro-resonator gyroscope, they found the device very sensitive to the rotation, and the enhanced factor here is nearly 10,000 times if you perform the detection near the symmetry breaking point. So as we can see in this picture from the right side, the panel B, the green lines here show is the symmetry breaking without any rotation. And once you start to rotate the whole siding, it will lead to a small detuning change for the counter-propagating waves. And one is shown by the blue, the other shown by the red. And you can see this very small detuning change will lead to a very large change in power. And you can easily detect the power differences by the photon detector, and you can know the rotation speed. So this is served as a kind of introduction to my project, and my current project is focusing on the counter-propagating waves. So based on this model, we model this sighting by the Lugia-Lato-Lefebvre equation. This is quite similar to the one that maybe you all know, but because the opposite group velocity, we should use different signs in the last term as shown in this equation 1. And next, I want to introduce some preliminary results that we found so far. So first, we start from the simplest case, the symmetric case, which means that we have the same pump in the two components. We have the same detuning and also the same wave. And for the continuous wave, as we know, the envelope is a constant, so which means the derivative of the coordinate and the respect to time is 0. So we can easily solve this whole equation, and we find the expression of the field, and by using this relation, we can draw the best stability plot. Yes, and as we know, to generate a frequency comp, we need the growing energy in the side modes. So therefore, we should study the modulational instability of this best stability plot. To do this, we can substitute the perturbation of the perturbate solution of this constant wave and into the previous equation and find its corresponding eigenvalue. And by checking the eigenvalue, we will know the stability of the certain mode along the detuning. So on the right side is actually the modulational instability plot in terms of the detuning and mode number. The bright region shows that the modes will be unstable in a certain range of detuning. Okay, so to see the comp generation from this continuous wave, we performed an example of dynamics at detuning here shown in about 10 megahertz. And the picture on the left side shows the simulation for the clockwise and counterclockwise components. And the one thing I need to make it more clear is that here we use the shifted coordinate because the waves in different components will propagate oppositely. So you need to shift the coordinates to make them to show them better. Just show them better. And the picture on the right shows the final spectrum of these dynamics. Okay, and at last, in the future, Yeah, we may make further study of the symmetry breaking of the counter-propagating waves, and also study the backscattering effect, and between the CW and the CCW, the counterclockwise waves in the microring resonator. Okay, thanks.
Thank you very much, Zhiwei. So now I'd like to invite questions from the audience to Zhiwei.
Just remember to turn your microphones on if you want to ask questions.
Yeah.
I'm sorry, how many minutes are left?
Yeah, you still, well, we have a couple of minutes for questions.
Okay, thanks.
Actually, you finished a couple of minutes before, so that's okay.
Okay, I'm just nervous that I'm speak too slow, so I accelerate my talk.
Yeah, Zhiwei, maybe I can sort of warm things up a little bit. So do you see a lot of connections between the work within the Microcomb and your previous work on cold atoms, or these connections are kind of superficial?
Excuse me? The connection between
do you see any connections between your work on cold atoms and the work in the Microcomb consortium?
Oh yeah, I think the major difference is that in the cold atoms you can start a different. I mean, the nonlinearity you can consider is much more, you know, you can consider dipole-dipole direction. You can consider the cold atom which which coupled by the microwave, something like that. So I think the nonlinearity in cold atoms is more different in compared to the Microcomb, because in Microcomb is actually in optics. In optics, you can consider in the Cat3 medium you have the Kerr effect, and actually Kerr effect is mathematically comparable to the contact nonlinearity in cold atoms. And but in cold atoms you can still have the long range interactions, right? So I think the physics in cold atom is much more fancy, or
well, I I'm not entirely agree with that. It's much more fancy, but it's definitely rich physics.
Yeah, different field.
In both areas. Yeah, in both areas it's very rich physics. But with microresonators, an obvious difference with cold atoms is that you have your losses compensated by pump, right? So in cold atoms, you're mostly concerned with balance between the dispersion of quantum packets and nonlinearity. But here on top of this, in microresonators, you have a balance between loss and pump, or even gain, right, if it is present.
Yeah.
Any other questions to Zhiwei? We still have time for 1-2 questions. Okay, so if there are no questions,
I have one now. Yeah.
Okay, excellent.
I was wondering about this gyroscope. I see many issues if you want to use this in an actual setting. So what kind of rotations could I actually measure with a system like this one?
Well, in this story, I just use it as an introduction. Yeah, we just find there's some fancy features here. So if you want to do it in experiment, I think you can, you can find this paper in the reference one, and they introduce in a very detailed way. So, yeah.
All right, thank you.
Yeah.
Could you send that link to me?
Of course, I can share it with you.
Thank you.
Yeah, they just did everything experimentally. Yeah, so maybe it's more information for you in the reference rather than my just a brief talk.
Yeah, that would be nice. Thank you.
No problem.
Okay, thank you, Evert. And thank you, Joey. And let's move on to the next presentation. And the next presentation is by Toby B. from Max Planck Institute in Erlangen. And yes, Toby, please go ahead.
Okay, let me pull up. Okay.
Please remember to share your presentation with us.
All right, can everyone see that?
Yeah.
All right,
Works
perfect.
fine.
Yeah, it's
Cool.
fine.
Okay, hey everyone. Hope everyone's doing okay considering the circumstances. So I'm Toby, and today I'm going to give you a brief, sort of introduction about myself. I'm going to talk about some of my educational history, so what I did in my master's year, and I think for my current research it'll be slightly different because at the moment, because Pascal just moved the group over here in January, so at the moment there's not too much research going on. So at the moment we're just building lab and doing some clean room fabrication. So I'll introduce more about some of previous work that they've done that might be relevant to everyone here. So who am I? So I come from New Zealand. So it's that little country down right by Australia, quite far away from Europe. So New Zealand has a population of around 5 million people. It's a relatively new country as well. I think it just became a British colony around 19th century. So in my free time, I like to play sports. I play rugby, I like to go hiking, and I'm also interested in network science and using complex networks to represent interesting data sets that's shown at the bottom right there. So my educational background. So I did my Bachelor of Science in Physics and Comp Sci 2016, and then I also did Bachelor of Science Honors in Physics. So that's kind of like it's like 75% courses, 25% research, and then I did my Masters as well at the Non-Linear Optics group at the University of Auckland. And so I'll present some research that I've done that I did during my Master's year next. So in my Master's year, we looked at magnesium fluoride microresonator parametric oscillations. So in this case, we are considering light propagation resonators, except instead of looking at frequency cones, we're looking at the generation of large frequency shift sidebands. So in this case here, we have the degenerate four-way mixing process, which produces an isolated pair of symmetrically detuned in-frequency sidebands from the pump. So these are phase matched using the higher order dispersion regime and also normal dispersion. So we get large frequency shifts. So what that means is that they are widely tunable. So with small changes in the pump frequency, you can get large changes in the sideband frequency. So this has been demonstrated in silicon microspheres. So as you can see here, the pump in the middle is only changed by tens of nanometers, and the sidebands, the anti-Stokes and Stokes, move by hundreds of nanometers. So one of the downsides of using the silicon microsphere is that due to its absorption at long wavelengths, you see that the anti-Stokes sideband starts to disappear at around 1900 nanometers. And so, and also there's a strong stimulated Raman effect. So one way to go about to sort of circumvent this is to use a different material. And so we used magnesium fluoride microresonators. So the good thing about magnesium fluoride is that it's transparent, has a wide transparency window from 0.2 to 7 microns. So it means that we won't get any of the problems that we see in silica microspheres, and it also has a narrow Raman gain. So we used a spheroidal geometry, which gives us a major and minor radius that we can use to engineer the dispersion. And these are some of the resonators that we used in our experiments. So they have major radii 0.5, 0.4, and 0.265 millimeters. And so the evolution inside the cavity is described by the LLE, and which is obtained by applying the cavity boundary condition on the NLSE. So when you apply linear stability analysis on the LLE, you can get the parametric gain side lobes. So these are the side lobes describe the frequencies that experience non-zero gain. Another thing that you can obtain from the small signal or the linear stability analysis is you can get the phase matching condition, which tells you the phase match frequencies or the maximum of this these side lobes. And so it's dependent, if we just truncate it to the fourth order, you can see there's a beta 2 and beta 4. So in our regime, we work in a normal dispersion regime with a positive beta 2, and a small negative beta 4 can counteract the group velocity dispersion so that this condition holds true. So what we see from that is you can get discrete, you can get discrete widely tunable sidebands. So this is, these are the phase matching curves on the left that you can get from that phase matching condition. So you just alter the pump wavelength and you can get the sideband or the phase match frequencies, and therefore the sideband frequencies that that satisfy that condition. So by reducing the diameter and changing the pump wavelength, we can get quite wide sideband. So they go from one micron all the way to 2.7 microns. So we don't see any of the downsides of silica where the sidebands past 1.9 microns would disappear, which is good. But we're also limited by the silica taper that we use. So any sidebands past that point, we couldn't actually detect. So one thing about these sidebands is that they're intrinsically discrete, because since you have to be pumping at a cavity FSR, the pump has to move in steps of 1 FSR to generate sidebands at wider steps, at wider frequencies. So what that means is that if you move the pump by 1 FSR, then the sidebands have to move by at least 1 FSR. So, and then FSR in this case is about 100 gigahertz or so. So in that case, it's not entirely useful to just have this discrete tunability. So one thing that we need is maybe some continuous tunability for each of these sidebands. So the parametric gain curve doesn't exactly describe the dynamics. So it tells you the maximum frequency gain, but it doesn't tell you this the sideband modes that are actually resonant. So if you consider the pump in the kth mode and then the sidebands in the k plus or minus jth mode, then you see that these cavity resonances described by the blue lines, they're actually, blue lines don't exactly match the phase match frequency. And so if you consider the cavity boundary condition, you can see that the odd orders of dispersion give you this new condition, and it's not dependent on intracavity power or the tuning, which indicates that the frequency shift of the sidebands from the pump remains constant while you're in the same resonance. So this is limited, however, by the narrow line width, but through thermal nonlinearity, the line width of the resonator will broaden as you approach it from the blue to tune side. So this allows you to stay resonant with outside the usual boundaries. And so what happens is that to remain at the same detuner, you need to change the pump by delta omega P, which considers the thermal optic and the linear thermal expansion contribution. And so if you shift the pump, then the sidebands also move. So with this, we can get around 12 gigahertz of continuous tunability. So what that means is that you move the pump by 12 gigahertz, and then the sidebands also move in the same direction by 12 gigahertz. Cool. So this means that you can combine the discrete tunability with this continuous tunability. So in conclusion of this part, we've shown parametric oscillations can generate widely tunable sidebands that span from 1 micron to 2.6 microns, and also some continuous tunability. So if you're interested in any of this work here, you can check out the group in Auckland at that link at the bottom. And some of this work is in this paper here as well. Oh, sorry. So moving on to right now. So where am I? We're in Erlangen, which is a small city or town, I guess, in Bavaria. So it's around 2 hours north of Munich by train and about 2.5 hours to the east from Frankfurt. And so it's home to about 100,000 people. It's quite small, but it has some big, I guess, corporations here. So Siemens, headquarters here, Adidas and Puma are close by. And it also has the Friedrich Alexander University of Erlangen in Nuremberg, which is where I'm a PhD student of. It also is home to the Max Planck Institute. So at the Max Planck Institute, there are, I guess, 4 main divisions. So there's the Russell Group looking at photonic crystal fibers. There's a Marquardt division looking at cavity optomechanics. There's a Sandoctor division looking at nano-optics, and then there's the group division looking at bio-optomechanics. And then there are several other independent research groups as well, which is where the Delhay group comes into play. So this is our group here. So this photo was originally taken in the UK, so that's why I'm not part of it. But yeah, so we're led by Pascal Delhay, and then the postdocs Leonardo, Jonathan, Shuang Yu, and the PhD students are George, Lewis, Niall, Andreas, and Michael. Some of them are still in the UK at the moment. I guess they're finishing up their PhD studies over there. So I'm going to introduce some of the work that they've previously done. So one is
Toby,
using...
you're a bit over time, so I can give you 2 more minutes, but then there won't be questions. Okay,
perfect. Let's see. Okay, so
yeah,
I'll just do this one. I'll just do this part then. Okay, so one thing is that one bit of work is that you could use an auxiliary laser to extend the range of accessing solitons. So what you do is you put another auxiliary laser, maybe quite far away from not far away, but you just put a auxiliary laser away from the pump. You put it on the blue detune side of your of the resonance, and as you scan the pump laser into resonance, it shifts all of the resonances. It red detunes all the resonances, which pushes the auxiliary laser out of resonance. But so this sort of maintains the intracavity power. But as you pass the 0 detuning point, you abruptly change into the soliton regime, and then the blue detuned auxiliary laser moves into resonance. So this extends the resonance range from the usual 100 kilohertz to 10 megahertz. So this means that the system only now has the Kerr effect instead of, you can only see that the bottom one the system only has the Kerr effect rather than any thermal effects, which makes accessing solitons much easier. So the figure E here shows that you can use a 780 micron pump to generate a soliton using this auxiliary laser. Okay, I'll just skip this. Okay, so what I've been doing is we've been doing some clean room fabrication. So we've been making some silicon nitride waveguides and also silicon microtoroids. However, the silica toroids, as you can see at the bottom left image here, right image has some defects. So our CO2 laser arrived last week, so we're starting to build the setup for that as soon as possible. And yeah, we're also building the lab. We have some fun team building exercises. So yeah, thank you for listening. Oh yeah, you can check out our stuff at this link here.
Yeah, thank you very much, Toby. Very interesting presentation, and so there is time for one very short question and very short answer, please. Okay.
Have this, I have one again.
Yeah,
If you're
good.
generating this microcomb with the 780 microwatt pump, how much power is then in this auxiliary laser?
It's so the auxiliary. I guess the power in the auxiliary laser, it doesn't. It just needs to be above the threshold to keep the sort of intracavity power the same. So in this case, for the 700 microwatt pump, I think the auxiliary laser was roughly the same. So for each of these cases here, let's say like the figure D, the 3 milliwatt pump was accompanied by a 2.5 milliwatt auxiliary laser. So all it needs to do is just keep the oh, sorry, I don't have the image. It just needs to keep it just needs to be able to maintain the intracavity power drop from when you go into the into this ESRs, the soliton resonance.
Yeah. All right. Thank you.
Oh, okay. Okay, thank you very much again, and let's move on to the third talk of the first session. And the third talk is going to be by Krishna Twaina from Chalmers University in Sweden.
Yeah, Dimitri, can you hear me?
Yes.
Yeah, then, okay,
yes,
I will share my slides. Yeah. Can you see my slides?
Yes, very well.
Okay. Yeah. Okay. Thank you, Dimitri, for my introduction. Hello, everyone. First of all, I would like to thank you all for your participation, and special thanks to Jonah and Dimitri for organizing this ESR introductory webinar session. I hope that everyone is safe and healthy amid these circumstances. My name is Krishna Twaina. I'm from Chalmers University of Technology, and I work in ultrafast photonics research lab. And my supervisor is Professor Victor Torres' company. So I would like to start my presentations talking about where I'm from. So you see, you may see your country in this map, but I would like to point out at this location. I don't know if you see the pointer here or not. So the country which is between the giant countries, China and India, a growing, economically growing country where I'm from. And this is the country, Nepal, where I'm from. So you know that there are 8 out of 10 highest peak in the world, and the highest peak, which is the Mount Everest, that which is located close to the China, and this you see the pointer there. And I'm from the capital city, which is the Kathmandu, also known as the city of temples. There are lots of temples that you see everywhere in the city, and we have a unique flag which is made up of 2 rectangles here in the corner, at the corner. And Nepal is also birthplace of Buddha, the founder of Buddhism. Now I would like to briefly talk about my educations and academic background. I did my undergrad, which is the Bachelor of Engineering in Electronics and Communications Engineering from Kopo Engineering College in Nepal. And I did my graduate, which is Master of Science in Microsystem Engineering from Masdar Institutes of Science and Technology in United Arab Emirates. And my master program was mostly focusing on integrated photonics devices. Talking about academic experiences, I have a couple of years of teaching experience back in Nepal in Advanced College of Engineering and Management, and I was a teaching assistant and research assistant in Masdar Institute of Science and Technology. Of course, the research assistant was part of my master's degree. And during my master, I had an opportunity to work in nano-optics and optoelectronics research lab known as NUR lab, where I spent most of the time doing characterizations and measurement of integrated photonics devices, fabricated in-house and foundry outside Chalmers. And my research scope is design, simulations, and characterizations of photonic devices. And my research interest is nanophotonic devices, spectroscopy, and fiber optics communication. So ultrafast photonics research lab at Chalmers is one of the divisions of a microtechnology and nanoscience department. And this ultrafast research group is led by Professor Victor Torres' company. And the mission of this ultrafast photonics research lab is to perform cutting-edge research in synthesis and manipulations of ultra-short light pulse for the various applications. Our expertise lies in developing the frequency-comb technology for applications in next generation's optical communication system and ultra-fast precision metrology. So the researchers in ultrafast photonics technologies are from different countries. We are quite small. We are 8, including supervisor, 2 postdocs, and 5 PhDs. As you see the flags here, so we are from 6 different countries. So ultrafast photonics research at Chalmers is almost independent in terms of resources and the equipments. However, we have a good collaborations with the different universities in different countries, and our research is mostly based on silicon nitride platform. As you see that silicon nitride offers us massive transparency window from 0.2 micrometer to 6.5 micrometer. Of course, we focus our research only around near infrared region. And talking about the work package, the work that is divided among the researchers in the ultrafast photonics research, some researchers are working on silicon nitride photonics or silicon photonics fabrications work, and some are working on nonlinear optics, mostly like simulations, and others working on measurement. Looking at my research scope, as you see here, the red one, I do some basic simulations of nonlinear optics and all sorts of experiment. However, having said that, I can't overlook the basic knowledge or importance of basic knowledge of the fabrications. So I should have a basic knowledge about the fabrication so that I can give the proper designs which is doable or can be fabricated in the clean room. Modelog microresonator frequency comb are broadly categorized into 2 types. One is bright solution comb and another is dark pulse comb. The bright solution comb occurs in anomalous dispersion regime where FSR increases as we move to higher order frequency, whereas dark pulse comb occurs in normal dispersion regime where the FSR decreases as we move to higher order frequency. You can see here the simulations result of a bright solution comb like this. It has a second envelope spectrum, and the bright pulse, which you see here like a spike or sharp line, which circulates around the microring resonator. Similarly, the dark pulse comb has a dark pulse, which looks like the diagram shown in the right side, and it circulates around the microring resonator. The downside of bright solution comb is that it has very low power convergence efficiency compared with the convergence efficiency in dark pulse comb. So the power convergence efficiency is very important when we talk about the long haul optical communication system, because we want to maintain the high level of optical signal to noise ratio. Moving on to my project work is about dark microresonator frequency combs for coherent optical communication system. Before talking about my project, I would like to talk about some milestone set by Ultrafast Photonics Research Lab. Back in a couple of years back, the researchers in Ultrafast Photonics Research Lab has demonstrated very first time the coherent wavelength division multiplexing transmissions for very long distance by using dark pulse comb in collaborations with the Purdue University. And And then last year, we have demonstrated the extremely high Q in microring resonators at 100 gigahertz repetitions rate by using subtractive processing method. So all the work so far we have been doing at erbium dope window, erbium band window, that means around C and L band. So which offers us, if you talk about the C band, which offers us around 5 terahertz of a bandwidth. So my project idea is to move from the C band or erbium band to thulium band. In thulium band, it offers us massive bandwidth, which ranges from 1.57 microns to 2.1 microns. That means we can get around 33 terahertz of a bandwidth, which is approximately 6 times higher than the bandwidth that we can get from erbium band. So the idea is to replicate the work that has been done in the Chalmers at erbium band to thulium band. So by using this massive bandwidth, we want to establish fully coherent link between transmitter and receiver to transmit the data at ultimate limit of fiber capacity. So this is the overall diagram of my project. So we are planning to use the dark pulse comb at both transmitter and receiver sites separately. Of course, those dark pulse combs should be identical and synchronize each other so that we can properly demodulate the signal. So the signal, the frequency line generated by dark pulse is used to modulate the signal at the transmitter side by using IQ modulators, and we multiplex those modulated signal, and we pass this massive tsunami of data through the microcore fiber, and at the receiver we demultiplex that signal first, and then the frequency line generated by another dark pulse comb is used to coherently demodulate or receive that signal by using coherent receiver. So this is overall idea of my project that I will be working on in near future. Right now I would like to briefly talk about what I have done in ultrafast photonics research lab. I have done some dispersance engineering simulations and some dispersance measurement in ultrafast lab, and I have built this precise measurement calibration setup by using Microcomb and interferometry based system in our lab. And I have done some nonlinear simulations such as a dark and bright pulse comb generations. And for the last couple of months, I have been working on sweep wavelength interferometry for precise calibrations of microring resonators. That means the phase and magnitude response of microring resonator. Once I finish this work, I will do some experiment related to frequency comb generations in ultrafast photonics lab. So I think this is the overall idea of my project and the work that I have been working on and what I have done so far. And with this, I would like to end my presentation. So you see, this is my contact information, so you can contact me at any time. So thank you very much for your kind attention and time. Follow the meeting. Yeah.
Thank you very much, Krishna.
Yeah.
Very good presentation,
You're
very
welcome.
interesting. And this talk is open for questions, please.
Yeah.
Yes, I do have one. This is Pascual Muñoz from UPB. So thanks for your presentation and your concept, which I am very well aware. I've been collaborating with your group a few months already. Can you come back to the slide where you show, yeah, that one, no, yeah, the next one, please.
Yeah.
No, the one that you show the concept with the multiplexers and the coherent and. Okay. Yes. I'm just wondering which is the ultimate goal or a number of wavelengths that you want to process.
So that depends on like conversion efficiency of a dark solution frequency comb that we able to generate, like a numbers of lines depends on how much power, minimum power that it has. If you look at here in this diagram, like if it consider the 25 lines, we would have only 0.5 dBm. Minimum power level is would be 0.5 dBm. So
Yeah.
of course, the numbers of line that we want to use or that we are going to use depends on the power conversion efficiency or minimum power level that we achieve. So far, I haven't no specific number, like I don't know the specific numbers, but of course it depends on the minimum power level when it generates the dark pulse comb.
No, for us that is important because as we will know down the road, we will be trying to design the multiplexers and the multiplexers for these kind of systems.
Yeah.
As my student will show later, so we would like to know this number and whether it is 10, 25, 40 or whatever. Okay. Thank you very much. Thank you.
You're welcome.
Yeah. More questions, please. We have time for one more question. Okay, if there are no more questions, then let's thank Krishna again and move to the last talk of the first session by Alexander Tusnin from EPFL. Alexander, please.
Hello, everyone. Can you see my screen?
Yeah, we can see your screen.
Great. So yeah, my name is Alexander Tusnin. I'm working at the laboratory of Professor Kippenberg at EPFL. And so I have two master's degree, one master's in physics from Novosibirsk State University in quantum optics, and I did it in parallel with the Polytechnical Institute of Paris, and it was master's in applied mathematics, where I also obtained engineering degree, which is analog of master of engineer. Also, I have obtained my bachelor's in physics in Novosibirsk as well, in physics of elementary particles. Here you can see just some nice pictures of my home university, Novosibirsk State University, and the one from Paris. During my studies, I had opportunities to work in 3 different institutes. The first one on the top is Budkin Institute of Nuclear Physics, where I worked on basically on experimental part of nuclear physics, and one of my duties was detector maintenance and data analysis from electron-positron collisions. In France, I worked in the Institute of Nanoscience and Cryogenics, where I investigated some advanced topics of magnetic-caloric effects. And my master's thesis I did in Institute of Automation Electrometry, which is in Novosibirsk as well, where I investigated theoretically plasmon forces which arise between two metallic planes due to plasmon interactions. I would like to start with my first project from Budkin Institute of Nuclear Physics, where basically I was working on the collider Web 2000 on the detector CMD3, which means cryogenic magnetic detector. And so basically, I was performing data calibration of the colorimeters and technical maintenance of the detector. And in parallel, I was analyzing data from the collisions. For example, one of such collision, its Feynman diagram you can see on the left, on the bottom left. And I needed to just employ some basic rules to try to find the most important, most relevant events for my research. In France, I was working on new magnetic caloric materials. In particular, I was investigating the role of dipole-dipole interactions in gadolinium lithium phosphide, and this role to Curie temperature. With this, it was pretty interesting because basically your dipole-dipole interactions, they depend on your lattice structure, and we were investigating how we were looking for optimal lattice structure for lowest Curie temperature, and maybe not lowest, but how to engineer the value of Curie temperature and to find the one that we need, because the magnetic caloric effect is maximal in the vicinity of this point, of this temperature. And my master project was about plasmon forces. So imagine you have two golden planes and you excite modes between them by an external laser, and it appears that at given polarization, TM polarization, you can have attractive force between these planes, and this force, if you use a laser at wavelength 155 micrometers at 50 microwatts, you can get the value of this force is about 1 nanonewton. And I was studying from theoretical point of view this force as a function of different experimental uncertainties. In the group at EPFL, in the group of Professor Kippenberg, we work on microcombs. So and so yeah, we work on chip scale frequency combs. And myself, I'm particularly interested in this DKS, this particular solitons, their dynamics and nonlinear dynamics itself. For now, I'm studying nonlinear dynamics in synthetic frequency dimensions. And I propose you for now to forget everything about solitons, about optics. Just imagine that your modes in the resonator, they in frequency space, they compose one-dimensional lattice. And if you have a phase electro-optical modulator in one part of the ring, you can couple these modes like in a real 1D chain, and this system will act as a crystal. But the main difference with solid state physics here is that in solid state physics, Dirac space is our just conventional coordinate, and reciprocal space is reciprocal space is space of wave numbers. Here it's the opposite. The direct space here is the frequency space, and reciprocal space is time. And it appears that measuring transmission trace of such a system, we can directly measure band structure of such systems. For example, here at picture C, you can see that when you have when you couple only nearest neighbors, you can see that transmission or transmission trace, or in other words, intercavity field response for different detunings directly represents the band structure. And here the question is, what happens if we have dispersion and kernel linearity in this system? So it means that we have just conventional electro-optical coupling, which is analogous to 1D chain, and plus nonlinearity for wave mixing. And I investigated this system first of all theoretically and then numerically. And my theoretical analysis have shown that in the presence of modulation, yeah, I found the modification to the nonlinear Schrödinger equation, and it appeared that the new governing equation for this mean field model appears to be just driven Gross-Pitayevsky equation. And I found that B-stable zone for this in presence of modulation bends, which is completely different to the case of conventional Chi3 for Chi3 nonlinearity. And so this zone bends, and solitons, they appear exactly at the top of the band structure. Here in solid lines, I present the width of B-stable zone, and using Lagrangian perturbation approach, I also achieved to obtain the soliton existence range, and it appears that just applying external modulation, we can manipulate soliton existence range by shifting it deeper in red detuning zone. Also, modulation provides electro-optical modulation provides with effective photon flags from the pump frequency, which allows generating of platicons without any avoided mode crossings or pulse pumping. We can generate it. So my simulations show that it's possible to generate them at relatively small powers, input powers. And another interesting outcome of this work is that due to modulation, new coherent structures appear in such nonlinear, in such synthetic space. You can see on the figure A, for example, for one-tone modulation, where I couple only nearest neighbors, that in the area where the group velocity of linear Bloch waves, which propagate along frequency space, is maximal, there are new coherent structures which you can see on the figure D. In blue, I present its amplitude profile, and red its phase profile, and their corresponding spectrum is presented on the figure E. You can see in blue I present the spectrum of these new structures, and green it is conventional EO-comp, which is similar to, in fact, to this, which is similar to synthetic space. But the main difference here is that the presence of dispersion, which leads to cut-off of the spectrum and appearance of such electro-optical comp. And this result shows us that due to kernel linearity, the translational symmetry in the frequency space is restored, and the linear coupling provided by electro-optical modulation is enhanced. If we use two-tone modulations, we obtain coexistence of stable and chaotic dynamics simultaneously. You can see such a special temporal diagram on the figure J, and corresponding spectral dynamics and nonlinear dispersion relation on the figure I. Here you can see that basically there are, on the left you can see one of the figure J, you can see a stable pulse which propagates without changing, and on the right there constantly appear different coherent nonlinear structures which interact with each other, and it's kind of breathing structure with the emitting of dispersive waves. So thank you for your attention.
Thank you very much, Alexander, for very interesting presentation, and thank you very much for keeping on time. And this talk is open for questions now. So, Alexander, I wondered what is on few pictures you showed numbers J1 capital, J2 capital. What are these? Are these numbers of resonators or something else?
It's a resonator width. In fact, it's measured in conventional, in conventional decay rate. So it's about I use parameters of our silicon nitride resonators. So here our resonance width is about 50 megahertz. So here it means J equals to 3. It equals to 25 megahertz.
Right, I see. Okay. Okay, thank you very much. Any other questions to Alexander? Yeah, we have time for a couple of questions. I think that's very interesting topic, right? The synthetic dimensions. And Alexander, maybe I can ask you. So have you thought about any topological effects? Because it's
I keep it in mind basically, because to get topological states here, I need to consider a chain of such. I need to consider a crow, so coupled resonators where I need with modulators. So to do that, I started to do this, but I don't have results for now because I'm just writing a solver for this problem basically.
Yeah. Yeah. Okay. Very interesting. Any other questions, please? Okay then. So thank you very much to all the speakers in this session. So now we have 10-minute break, and after this 10-minute break, we reassemble for a second session, and it will be chaired by Inga Brüning, Professor Inga Brüning from Freiburg, right? And we are looking forward. And now we can either have a free time, or maybe some of you want to ask questions, you know, to presenters. So yeah, by all means. So now we reassemble at 13:05. Sorry, at 13:15, at quarter past. Yeah, at 13:15 in 10 minutes. And well, I have a question to Toby. Toby, I had a question about. Can you hear me?
Yeah, I'm here.
I had a question about the quality factor for this experiment, which was published in Nature. For this, you know, 5-way sidebands. So what was the quality factor? Do you remember?
The quality factor. A finesse is roughly 50,000. So the quality factor range from like 0.5 to 1.5 times 10 to the 8.
Right, 10 to the 8. I see.
Yeah.
I see. Okay. And was it much different for the pump and for the sideband?
Oh, yeah. Well, I guess as it got further out, the pump was a little bit different from the sideband, but it was all within like 10 to the 8.
Okay. Okay, then thank you. So it's not actually the very high quality factor. It's quite.
Oh no, the quality factor wasn't too high.
Yeah, I see. Okay, thank you.
No worries.
Could I just say something regarding Dimitri, your initial